Math 121, and this packet is still going to be dealing with the z-scores table. Remember I said all of our remaining sections, once we introduced this, would require this in some capacity, so we'll still be using it, right? So let's take a look. I've got some hints first. The central limit theorem, that's the main topic here, see below, I just abbreviate it, deals with using the normal distribution, right? Everything here is normal, right? Normal distribution, to talk about samples. We're going to be talking about whole samples. We want to talk about samples rather than individual data points. For example, if I have a class, a sample, with 35 students in it, can I use this normal table, this normal distribution, to determine anything by using what I know about the population? However, in previous sections, we talked about a single student, a single data value. That's the key difference here. We're going to be talking about groups instead of individual data points. Now, the central limit theorem says, for all samples of the same size n, so we're taking samples, and the samples are bigger than 30. So let's say that after 10 years of teaching here at North Country, I've had a whole bunch of classes with 35 students in them. I can use the properties of this section to draw conclusions about the groups of students instead of just individual students. I have a bunch of different samples, all with the same size. The sampling distribution of the mean, of the average. So I'm also looking at averages. Normally we look at x values, right? Notice we're looking at x bars. Can be approximated by a normal distribution of mu and a standard deviation of sigma over square root of n. All this theorem is saying, in less mathematical terms, is we can look at samples now instead of looking at individual data points. Now, there's a few things here we need. So in order to use the central limit theorem and to talk about these averages, we need some new things. So the first is a population. We have some population with any distribution. The population does not actually need to be normal necessarily. And the population has a mean of mu and a standard deviation of sigma. That's pretty standard as well, right? That's the symbols we use for the average and the standard deviation for a population. So we've got a population. And then you've got some simple random samples, all that have n people in them. We're looking at samples with n people in them from the population. So we have some population, and we have some random samples we're taking from that population. We have some requirements. You only need to meet one of the requirements. Keep that in mind. You only need to meet one of these. So either the population is normal, or your samples are all bigger than 30. Either one of those allows you to use the techniques here, because we're not actually talking about the population, we're talking about the samples. So if n is bigger than 30, we can use a non-normal distribution. But if n is smaller than 30, it needs to be normal. It needs to be one or the other. There's one requirement needs to be met. Then, the mean of all values of the sample means. This is the mean of the means. The symbol we use is a mu with a little x bar written like below and to the right of it. This symbol is pronounced mu sub x bar. This symbol here is pronounced mu sub x bar. It's because it's a subscript. Mu sub x bar is how you pronounce this symbol. It's the average of the averages. Now, what's the formula for this? Well, the average of the averages is always going to be equal to the population average. The average of the averages is equal to the overall population average. The mean of the means, the mean of the sample means, is equal to the overall population average. That's a pretty nice formula. You can just transfer the numbers back and forth. Unfortunately, standard deviation will not be. So here, we're looking at the standard deviation of the sample averages. The symbol for this one is a sigma with a little x bar next to it. Same thing, it's pronounced sigma sub x bar. So if you want to write that down, sigma sub x bar, that's the name of the symbol. This, the sigma sub x bar, is equal to the original standard deviation divided by the square root of the sample size. So you got to square root your sample size and you got to divide. The standard deviation of the averages is the overall population average divided by the square root of the sample size. These two numbers will be what we use when we do our z-score. Now, our new z-score formula is going to be that x bar minus mu sub x bar over sigma sub x bar. That is our new z-score formula. Remember, the original z-score formula is z equals x minus mu over sigma. Notice I'm just using x bars because I'm talking about averages rather than an individual x. I'm talking about an overall average. So I need to calculate these two numbers when I go to do this. Now, we have a caution. If the original population is not normal and the sample is 30 or smaller, then the distribution of the means cannot be approximated by a normal distribution. This section does not apply. Remember, there's requirements. It has to meet one of these. If it fails both, right, then you can't use these techniques. Sometimes a question might be, apply the techniques if possible. Perhaps you can't apply the techniques, in which case there might be an option in a multiple choice question that says the techniques cannot be applied because blank. And you would identify why. Make sure you understand there are requirements you have to double check before you can use these techniques. So we've got a couple formulas. Let's take a look on the next page what we got. The next page says, how do we work with these? Considerations. How do we problem solve here? Well, the first step, like I said, is check the requirements. When working with the mean from a sample, verify that the normal distribution can be used by confirming the original population is normal or the sample size is greater than 30. You double check those requirements, right? You double check that you meet the requirements. Then you ask yourself, are you talking about an individual data value or a mean from a sample? So you determine whether you're using a normal distribution with a single value x or the mean x bar from a sample of n values. Are you talking about a group of people or a group of subjects or one subject? If you're talking about an individual value, this was covered in section 6.2, and the formula you use, remember, is the standardization formula, x minus mu over sigma. We've already done individual values. That's from the previous chapter. Now, if we're talking about a mean from a group, a sample of values, then we need to make some changes. We need to use sigma over square root of n as the standard deviation. So here, we use the new formula that z is equal to x bar minus mu sub x bar over sigma sub x bar, which could also be rewritten as x bar minus regular mu, because on the first page we learned these two are equal, right? These two are equal. Over, in the bottom we'll have sigma over square root of n, because sigma sub x bar is sigma over square root of n. Sigma over square root of n, right? We use the new formulas we just covered. Now, this sigma sub x bar is also called the standard error. We call this the standard error. That's the name for it. Notice it's standard, like standard deviation, and it's called standard error because when you take a whole group of samples, you minimize your error. Sometimes it's denoted SEM. I believe that stands for standard error metric, but I'm not totally positive. I just use the word standard error. It also is sometimes abbreviated ST.err. for standard error. This is common in a lot of programming languages. Just different ways you can look at the terminology, right? But the symbol is sigma sub x bar. Now, caution. Be super careful when you determine whether to use the central limit theorem or the techniques for standardizing a normal curve from the previous section. The major difference is what is the subject of the question. Is the question asking for information about an individual subject or about a group of subjects? That's the key. Are you talking about one data point or a whole group of data points? For this reason, reading carefully will be super crucial because these questions are going to be worded extremely similarly to questions we've already seen. There's just going to be a slight flip to them. And we'll see that on this next page. So let's take a look. Let's look at an example. This example has to do with elevators. The elevator in the car rental building at San Francisco International Airport has a placard, a sign, right? Placard is a sign. It's got a sign that states the maximum capacity is 4,000 pounds or 27 passengers. You've probably seen signs like that in an elevator before. Now, if I take 4,000 and divide it by 27, I got 4,000 pounds and I can fit 27 people in that elevator. That's a 148.148.14. That converts to roughly a 148 average weight, right? If I cram 27 people into it, they can each weigh 148 pounds before I'd overcap the maximum weight, right? Let's assume a worst case scenario. What's the worst case scenario? Well, people come in a few different classifications. And, children versus adult. Who tends to weigh more on average? Adults, right? Male versus female. Who tends to weigh more on average? The data implies males tend to weigh more on average. So if we're trying to use the data to imagine a worst case scenario, we're going to fill the elevator with 27 adult males. We're going to put 27 adult males in my elevator. I underlined mean in 148 as well. Now, assume that adult males have weights that are normally distributed, oh that's good, with a mean of 189 pounds and a standard deviation of 39 pounds. So, my population of adult males has some information. I'm going to write that down here. So, adult males have an average weight of 189 pounds and a standard deviation of 39 pounds, right? And I also know some other things. So let's see. Let's see what else we might want to pull from this question. Let's read what it's asking. Step 1 says, find the probability that a randomly selected adult male has a weight greater than 148 pounds. I ask myself, is this question asking about one male or a group of males? It's a single male, right? This first question is actually the techniques from Chapter 6.2. This is not a new question here. So let's look what it says. It says find the probability. Well, I'm finding a probability using the normal distribution, so I should draw my favorite picture. In the middle, you always put your average, which is 189. And then, what's my data value of interest? My data value of interest is 148, right? I want to find the probability that my random adult male weighs more than 148. Well, that's going to be somewhere around here, right? 148. And I shade greater than would be to the right. So I shade to the right. Now, remember, when you have non-standard measurements, you need to convert them. The average always becomes 0, and I need to calculate the z-score for the other one. 148 minus the average divided by the standard deviation, which is 39, gives me the z-score, right? So let's check. 148 minus 189 equals, divided by 39, gives me negative 1.05. negative 1.05. So I get a z-score of negative 1.05. Now next, remember, next you always want to look in your table. So let's pull out our table. We're looking for negative 1.05. Negative 1.05 gives me 0.1469. So my table gives 0.1469. This is not my answer, because what's the trick? The trick here is I need to subtract from 1, right? It's shaded to the right. So I'm going to subtract from 1. Gives me 1469. Gives me 8531, I believe. Let's subtract 1 minus 0.1469. 8531, yes. 0.8531, or 85.31%. So what this first part tells me is there is an 85.31% probability that a single adult male has a weight greater than 148 pounds. That is the answer to the first part, right? Find the probability a randomly selected adult male has a weight greater than 148 pounds. There's an 85.31% probability that a single adult male has a weight greater than 148 pounds. That makes sense, right? The average is 189. You'd expect it to be a decent chance that that person weighs more than that, right? That just makes sense. Now, the second part is going to be different. Let's see. Find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148. Now, what? 27? That's smaller than 30. My group needs to be bigger than 30. I can't do this. Oh, but I can. Because what's the other requirement? The population is normal, right? That's the other requirement. I have a normal distribution, right? Either this number, the sample needs to be bigger, or the population needs to be normal. So, additionally, I know my sample size, remember n is your sample size, is 27. The sample size is 27. So now when I go to do the second part, once again, I am going to need to consider some things. The first thing I need to consider is, am I talking about an individual or a group? Clearly a group, right? It's a sample of 27 people. So because I'm working with a group, I'm going to compute mu sub x bar, which remember the formula is equal to mu, which will be 189. And I need to compute sigma sub x bar, which is going to be equal to the old sigma over square root of n, which plugging in gives me 39 over square root of 27. So I'm computing my standard error. Because I want to talk about a group, I need to change the standard deviation into a standard error. I got a square root before I divide. Remember, square roots are exponents. You got to do that first. So the square root of 27 is 5.1961524. So I get 5.1961524, and that's under the number 39. Now I can divide. 39 divided by 5.1961524 gives me 7.51. I'm going to round to 2 decimal places. 7.51. My new standard error that I am going to use for this question is 7.51. I calculated these two numbers first. this one wasn't much of a calculation, right? It's just the same as from the other part. But I had to calculate the second part. I'm going to use these two numbers in this second half because I'm talking about a group. So what about my group? Well, I want to know that their average weight is greater than 148. So I'm going to draw my favorite picture, which the mean, I use this number, the new number. It's the same, but I want to make sure I emphasize you're using these newly calculated numbers. So 189. The data point of interest is still 148. And I'm still looking at greater than, right? Still looking at greater than. So I'll shade to the right. I'll shade to the right. Now, I need to calculate z-scores. The middle is always 0 for a z-score. That never changes. However, calculating this z-score, the z-score, I need to use my new formula, x bar minus mu sub x bar over sigma sub x bar. So my z-score will be, let's see, the value of interest is 148. That's what I want my gentleman's average weight to be greater than. Minus the newly calculated mean was 189. Over, I use the 751 now. 7.51, because in the formula you use standard error. You don't use the standard deviation anymore. You now use your newly calculated standard error. This is the twist, right? I said there's going to be a twist in the question. The twist in the question is we're using new values in our z-score formula. Now, when we go to compute that z-score, we get 148 minus 189. Negative 41 divided by 7.51 gives me negative 5.46. Negative 5.46. That's my z-score, which I can look up in my table, right? Once you calculate your z-score, you look it up in your table. Let's see, negative 5.46. That's 3.5 or lower, right? So I'll use 0.0001. So my table gives me 0.0001, but I'm shading to the right. When you shade to the right, you got to do 1 minus 0.0001, which gives me 0.9999, which is also equal to 99.99%, right? Decimals to percents. So, using the information I just got, I just found that there is a 99.99% probability, I'm going to abbreviate it prob, that a group of 27 adult males has an average weight of 148 or greater. That is the answer to the second question. Notice my number changed. That should make sense. If a single adult male has an 85% chance that they will have a weight greater than 148, it should make sense that a group of 27 of them will have a higher probability that their average weight is 148 or greater, right? That's how, think about it. If each part has a high chance of being bigger than the number in question, and you average them all together, it's got a high chance of being bigger than the number in question still, right? An even higher chance. We're talking about the whole group now. So notice we talked about an individual person in the first part and a whole group of people in the second part. That is the key difference between these two competing concepts. The central limit theorem applies to groups of people. These methods of standardization from section 6.2 apply to an individual, one data point. Make sure you keep that in mind. Are you talking about an individual or a group? Now, is the elevator safe if you want to put 27 adult males in it? No, right? We learned that the average weight has to be 148 or lower for the safety sign. This number right here tells me there's a really high chance that my 27 gentlemen will have an average weight that is exceeding the weight limit. So, maybe the San Francisco International Airport should reconsider the name of that sign, or the information on that sign. Either they have to change this number from 27 passengers, or include some other information, right? There's misleadings here, right? It's not a truly representative safety sign. The 4,000 pounds, that can be true, right? You know, you can determine at what weight limit the elevator would break. The 27 passengers is the number that's iffy, right? That's where we have some issues. So, that second part uses our new techniques. Let's take a look at another example of these new techniques. That's going to be slightly different. Now, let's take a look here. It's body temperatures. We're going to assume that the population of human body temperatures has a mean of 98.6 degrees Fahrenheit. So the mean is equal to 98.6 degrees Fahrenheit. You've probably heard that before, right? I know I have. It even says, as is commonly believed. Also assume the population standard deviation. So the population standard deviation is equal to 0.62 degrees Fahrenheit. If a sample of size n equals 106, well, right away, I'm going to note in my head that I'm talking about a sample. It said so right there. I'm not talking about an individual, I'm talking about a sample. If a sample of size n equals 106 is randomly selected, so I randomly chose 106 people, find the probability of getting a mean of 98.2 or lower. So my X bar is supposed to be 98.2 or lower. Right? We don't really write them much like this, but you could write it like that if you wanted. This is the thing of interest, right? Mean of 98.2 or lower. I'm looking for the sample mean to be 98.2 or lower. Now, I'm going to draw the picture first. So I'll draw a normal curve. In the middle, always goes the average, the population average, 98.6. The value I'm interested in researching is 98.2 or lower. So I'll put a little bar here for 98.2. And it's lower, so I shade left. And now we're ready to start looking at what's going on. The z-score for the mean is always zilch. However, I can't calculate my z-score for this yet. I need to calculate my new average, my average of the averages, right? I need to calculate my mu sub x bar, which is always equal to mu, which is 98.6 degrees Fahrenheit. That never changes, right? But my new standard error, I'm going to do standard error, right? Sigma sub x bar is equal to sigma over square root of n, which is equal to 0.62 over the square root of 106, which is equal to 0.62 over the square root of 106. 106 square rooted is 10.29563. 10.29563. 10.29563. So I'll divide that. 0.62 divided by 10.29563 gives me 0.602. 0.0602. I'm going to round there. 0.0602. That's my new standard error. I use this number instead of the standard deviation because now I can calculate the z-score for the 98.2. I have to do this because I'm looking at a sample now. A sample mean, right? I'm looking at a whole sample. Well, 98.2 minus the average, right? 98.6, and you divide by your new standard error, 0.0602, will give me a z-score of, let's see, 98.2 minus 98.6 gives me negative 0.4 divided by 0.0602 gives me 6.64. Negative 6.64, which the table, right, if I look in the table, is going to give me 0.0001. We saw that earlier, right? Negative 3.5 and lower is 0.00001. 0.0001. So that's my table value. So this means there is a 0.01%. This decimal as a percentage is 0.01. There's a 0.01% probability that a random sample of size n equals 106, that was my sample size, right, has a mean of 98.2 or lower. I should include degrees Fahrenheit on that 98.2. So it's highly unlikely that this happened, right? That is extremely unlikely. So if I was conducting research and collected a sample of 106 people and they had an average temperature of 98.2 or lower, that's highly unlikely, according to this calculation. That means one of two things has to be true. Actually, one of three things, but the third one is less likely. The first two options. The first is my sample is unusual. My randomly selected sample, what's the population? Is it the whole population of humans? Or did I randomly sample hospital patients or something? Or did I randomly sample children? There might be something with the sample, right, that would cause me to have weird data. That could be possible. But if I collected the sample well, what could be another error? Another error might be that the 98.6 assumption was wrong. And we actually have been finding information that implies that the average human body temperature isn't actually 98.6 degrees Fahrenheit. That seems to be the case. Data seems to be suggesting it's actually a smidge lower than that, as we've been collecting more and more data. And the third possibility, the less likely option, is that my population data wasn't initially accurate, right? But if I'm trying to prove something about the population, I can use data we've already found and find issues as well, right? There's some things that could be going wrong, right? Something is funky. This is unlikely to have happened. So I need to consider what's going on here. So, that brings us to the end of this section. That brings us to the end